Hello, class. Mr. Bean here. We're going to continue on with our video 12 discussion, uh, Newton's universal law of gravitation. This will be part two of the video, and we want to it's titled little g or gravitational fields, which is little g. So on here, we'll let you go ahead and read this part here for further reading. And I'm going to kind of like talk a little bit about what this is here, what the mathematics are, and we'll go ahead and see what we got going on here. All right, so let's go ahead and click on this here. And so from where we just finished, we know that Newton's law was developed to look like this. All right, equal sign here, equal sign, and it's going to be big G, and it's going to be mass 1 times mass 2 divided by their distance squared from the center of each object. Okay. All right. So in this example here, let's go ahead and assume like we have the Earth. So let me go ahead and get shapes here, and let's go ahead and make like the Earth. And we'll make it a little bit fatter in the middle. Okay, good. All right. The Earth is a little bit fatter across here. So the diameter this way is greater than this way. Okay, because of the tidal bulge. All right. Anyway, so let's go ahead and take a quick look here, and let's go to drawing here. Okay, so let's say we have a person standing right here on top of he's standing right here, and from the center here to here is the Earth's radius. Okay, so this is the radius of the Earth right here. All right, and we want to find out how much do you weigh? So how much do you weigh? Okay, which is a valid question because we do this almost, everyone's done this before. And so we're going to figure out what does this mean here. All right, so take a look at this equation right here. In fact, we're going to call this here the mass of the Earth right here. And this person here will be mass 2. We'll call that mass 2. And this here is the mass of the Earth, like so. All right, so what we have here is, I'm going to go ahead and change colors. Let's use black here. So take a look at this part right here. So if I was to take just this part right here, and let's kind of bring it over here. We have a value here we have what's called big G, now a gravitational constant. We have here the mass of the Earth, and we also have the radius of the Earth squared. Okay, this is to the surface here. Okay, or the mean radius here. Now, all this here is called little g. Little g. Okay. Now, if I was to put all the values in here for g, okay, so let me go ahead and pause here real quick. All right, so here we have the Earth's data here. Let me go back to drawing here. So we have the Earth's data. So if I was to put the mass of the Earth in here, the gravitational constant, right, which big G, which remember now is, was it 6.77 times 10 to the minus 11, right? Hold on. Ah, G is big G is equal to 6.67. All right, getting a little Alzheimer's here, times 10 to the minus 11. So it has this value here. If I put that in here, and also put it in the Earth's radius, right here, the Earth's radius here, the Earth's radius, the Earth's mass. Notice this is in meters and kilometers. And if I put all these values in, guess what I get? I get G is equal to 9.80 meters per second squared. So that's where this value here comes from for little g. Okay, so when someone asks you how much you weigh, they're really asking you what's your gravitational force of attraction to the Earth. Because here we have weight, right? Weight is, and this is this person's mass. So this will be mass 2, and this will be times g. So this here is the gravitational field strength right here, is this value little g. Okay, and that's also the same value we use to find someone's weight, or whenever we use anything with g, little g, it's 9.8 meters per second squared, and it comes from right here. Okay, now some things to consider about the field strength. Okay, so let's suppose this here is the surface of the Earth, and let's say we have a satellite up here, right? And here's a satellite, and let's say it's moving in this direction around the Earth here. So we know from the center to here, this is the radius of the Earth, right? Okay, and now from here, there is some altitude, right? Now you could say A for altitude here. Okay, so if I want to calculate the gravitational field strength here, right? We'll call it G prime because it's a little bit different here. We'll call it G prime here. That's going to be, of course, is big G, right? It's going to be the mass of the Earth. That does not change here, mass of the Earth, divided by, now this time, it's going to be the radius of the Earth, right? Radius of the Earth plus this altitude here. And make sure that everything's in meters. Got to be SI units, right? We're going to say SI units here, okay? And it's got to be squared. So this is what the gravitational field strength is here. So the higher up you are, as you increase the radius here, this number gets bigger. Therefore, this value gets smaller. So further you are away from the Earth's center, uh, the uh, the gravitational field strength decreases. Okay, and here's why it decreases, right? So let's say here's a mountaintop here, right? Here's a mountain here, and someone's standing here, right? Someone's standing here, and someone's on the surface of the Earth here, right? This here would just be the radius of the Earth, right? Here. And this here would be the radius of the Earth plus whatever this altitude here is. We'll call it maybe A1. So you can see here the gravitational field strength here is less than here because of this increased distance here. Okay, so that's the take-home message regarding the gravitational field strength. So what I just showed, notice the units here. See how it's, if you go ahead and read this here, sometimes, especially on the simulations that we use here in class, you'll see this, Newton kilograms, okay? And so if we were to work that out, 9.8, and here we have newtons per kilogram, right? Okay, so way to look at that is maybe put newtons over 1 here times 1 over kilograms. That way we can kind of see what's going on. Equals. So newtons, remember, is kilograms, meters per second squared times 1 over kilograms, like so, right? So here the kilograms cancel out and we get meters per second squared. So that's just another way to discuss gravitational field strength is newtons per kilogram, but we also know is meters per second squared. Okay. All right. So this is a good reading here. So you may want to go ahead and kind of read this a little bit more and see what's going on here. It's worked out again, and we have it here as well. And we have some more value. Here's 9.8. Here's that example that I didn't want to do that labors calculation here because there's a lot of calculating here. Notice SI units, SI units, SI units. Okay. All right. So we'll go ahead and pause, and I'll go ahead and let you do this problem here. Okay, all right, take a look at, so here's 8.7. It's already worked out for you. So take a look at this, and here's the answer here, so I'll give you an example here of how to work it out. Here's another example, 8.8. The answer is worked out for you here. Now here's 8.9. We're going to go ahead and pause here. I'm going to go ahead and let you work out 8.9. Okay. Here's 8.10. I'm going to go ahead and have you guys work out 8.10. Okay. And hit pause. Okay. Have you guys work out 8.11 here. Pause. Okay. Let's go ahead and scroll down. Here's 8.12. It's already worked out for you guys here. So you can see the calculations involved and what you need to do. Here's 8.13. Okay, I like this one here. A little conceptual, so we'll let you guys go ahead and do 8.13. Now make sure you're looking at the feedback that I provide. Okay, all right. Go ahead and scroll down some more. And here we'll go ahead and end here, and we'll go ahead and stop for this video.